Hello, my awesome chemists. Hope you're having a wonderful day so far. We're going to talk about electron configurations today. So electron configurations are kind of like a map that show us the distribution of electrons among the orbitals of an atom. So distribution shows the distribution of electrons among the orbitals in an atom. And remember that we said electrons are very important in chemistry because the movement of electrons cause chemical reactions, and so it is really important to know kind of the address of the electrons and where they are, what energy levels, sublevels, orbitals, and all that stuff. So the electron configuration is kind of like a map to show us that. If you remember last time, we talked about the Offbot diagram or the orbital diagram, and we showed that the numbers represent our energy levels, so 1, 2, 3, 4, 5, 6, and so on, and the energy increases as you go this way, away from the nucleus. First energy level is the lowest, then the second, then the third, then the fourth, and so on. Then the letters represent the sublevels, so S, P, D, and F. Theoretically, there's a G and an H and so on. And each of these sublevels have orbitals. The S's have 1 orbital, the P's have 3 orbitals, the D's have 5 orbitals, and the F's have 7 orbitals. And these orbitals are represented by these lines here. And we said that within the same energy level, like let's look at the 4th energy level here, the S's are lowest in energy, and then the P's, then the D's, then the F's, and that's because of the number of electrons that can occupy these sublevels. S's have 1 orbital, so they can hold up to 2 electrons. P's have 3 orbitals, so they can hold up to 6 electrons. D's have 5 orbitals, so they can hold up to 10 electrons. And then the F has 7 orbitals, they can hold up to 14 electrons. So you can see that the more electrons we hold, because they repel each other, the more energy we need for those electrons to stay there. I do want you to notice the order that, you go 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d. You'll notice that in general, the 3rd energy level is lower in energy than the 4th energy level, right? But not all the sublevels in the 3rd energy level are lower in energy than all of the orbitals or sublevels in the 4th. What does that mean? Look at this right here. You'll see you go 3s, 3p, then 4s, and then 3d. So the 3d is actually higher in energy than the 4s. That's kind of interesting, right? I'm from Egypt. People in Egypt tend to be shorter than the people in the US, right? So on average, the people in the US are taller than the average person in Egypt, right? But there might be one person in Egypt that is taller than one person in the US, right? So on average, the 3rd energy level as a whole is lower in energy than the 4th energy as a whole. But the 3D sublevel has such high energy that it surpasses the 4s. So the highest sublevel in the 3rd energy level is a little bit higher in energy than the lowest sublevel in the 4th energy level. Does that make sense? Hopefully it does. But anyway, this is the order of the energy. And so you'll notice we don't fill the whole 3rd energy level first before we start the 4th. We actually go 3s, 3p, 4s, 3d, and so on. So this is the order that the electrons actually fill up. So there are 3 principles that we've come up with to explain what we've observed about the electrons filling in these orbitals. So the Offbot principle is just what we were talking about. Electrons are added one at a time to the lowest energy orbital until all the electrons of the atom have been accounted for. So we go lowest energy orbital. And remember, Offbot means build up in energy. And so this is the order that we go by when we fill in the electrons. You'll have to know this order for now. Tomorrow I will show you how to get that from the periodic table. Just by looking at the periodic table, you'll be able to tell what the order is. So you don't have to really memorize this. You can just look at this to do your homework for tonight, the worksheet, but then tomorrow you'll be able to look at a periodic table and be able to tell. So again, the Offbot principle, building up an energy, we're just filling it up in terms of energy. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, and so on. The second principle is the Pauli exclusion principle, which says an orbital can hold a maximum of 2 electrons. We already know that, right? To occupy the same orbital, 2 electrons must spin in opposite directions. And so we show that. We've kind of already shown that last time by, if this was my orbital, I show 2 electrons, one looking up, one looking down. In reality, it's not that one is spinning up and one is spinning down. They're just spinning in opposite directions. Why would they spin in opposite directions? Because they repel each other. So they want to be as far away from each other as possible. And then finally, Hund's rule, which says electrons occupy equal energy orbitals so that a maximum number of unpaired electrons results. What does that mean? So let's say I have a 3D sublevel that has 5 orbitals, right? And so 5 orbitals, I can hold up to 10 electrons, right? Well, let's say I only need to fill in 6 electrons. What I do is I start by putting an up arrow in each of them first. So 1, 2, 3, 4, 5, 6. So I put one up arrow in each of the orbitals first before I go and start pairing them up. As opposed to, so this is the correct way, as opposed to this. 1, 2, 3, 4, 5, 6. This is not correct. That's what we've observed that the electrons do. They fill them up by being placed 1 electron in each of the orbitals first before they pair them up, as opposed to this. Why? Why do electrons do that? Well, if you think about it, electrons, again, repel each other, right? If we put them like this, where they're paired together in a small area, they're going to repel each other more than if you put them as far away from each other as possible. And so you want to kind of spread them out, put 1 in each of the orbitals first before you go back and pair them up. So let's practice a couple of these. We're going to do the orbital diagram for oxygen and for nickel. So we're going to start with oxygen. So oxygen has 8 electrons total. And I'm going to do it just because it's easier for me. I'm going to do it like this, just in all one line. If you choose to do it this way vertically, that is fine as well. So I'm going to start with the first sublevel, which is the 1s. The 1s only has 1 orbital, and it holds up to 2 electrons. So there are my 2 electrons. Next, I go to the 2s. The 2s only has 1 orbital, and it takes up to 2 electrons, and I need both of those. Okay, I've drawn 4 so far. The next sublevel is the 2s, or sorry, the 2p, I apologize, 2p. And I'm getting this order just from my diagram here. I'm just following either this diagram or this diagram. So you go 1s, then 2s, then 2p, then 3s, then 3p, and so on. So I'm just following that order. So I go 1s, 2s, then the 2p. The p has 3 orbitals, right? So I can hold up to 6 electrons. Do I need all 6? No, I only need 4 more. So 1, 2, 3, 4. Remember, you put 1 in each first before you go back and pair them up. So this is the Offbot diagram for oxygen. If you add up all the arrows, that should equal to 8, because I have 8 electrons and these arrows represent the electrons. Let's try nickel. Let's see, nickel is right here. It has 28 electrons. So nickel, 28 electrons. Let's do that. So we're going to start with 1s. That takes up to 2 electrons. Then 2s. That takes up to 2 electrons. Then 2p. That takes up 6 electrons. 1, 2, 3, 4, 5, 6. So far I've drawn 10 total electrons. 18 more. So next, what comes after that? 3s. Holds up to 2 electrons. I've drawn 12 so far. Next, look at your order. You'll find 3p. That takes up to 6 electrons. So far, we've drawn 18 electrons. 10 more. What comes after the 3p? 4s. Takes up to 2 electrons. What comes after 4s? 3d. 1, 2, 3, 4, 5. The 3d has 5 orbitals. I can hold up to 10 electrons, but how many do I need? I only need 8 more because I've already drawn 20, right? So 8 more. So 1, 2, 3, 4, 5, 6, 7, 8. So that is the Offbot diagram for nickel. It shows me every single electron in nickel. It's kind of like a map, what energy level, what sublevel, what orbital, and what spin. So both the Offbot diagram and the electron configurations are maps that show the distribution of the electrons among the orbitals in an atom. If I ask you for an orbital diagram or an Offbot diagram, I want you to draw these with the arrows and everything. If I ask you for the electron configuration, it's a little bit of a shortcut. It's the same thing, but just a little bit of a shortcut. Let me show you. So let's do lithium. And we want just the electron configuration. So lithium has, if you look at the periodic table, has 3 electrons. So I start the first lowest energy sublevel is the 1s, right? So I write 1s. Instead of drawing the line and the arrows, what I do is I put a superscript that describes how many electrons go there. So my 1s takes up to 2 electrons, right? So instead of drawing 2 arrows, I just put a superscript 2. This is equivalent to this right here, just a little bit of a shortcut. Okay, that takes 2 electrons. I need 1 more, right? So I go to the 2s. The 2s can hold up to 2 electrons, but I only need 1. So the electron configuration for lithium is 1s2, 2s1. If I add up my superscripts, I should get the total number of electrons. So 2 and 1 is 3 electrons. Let's try carbon. Carbon has 6 electrons. So I start with my 1s. How many electrons can I put in the 1s? I can put 2 electrons. Then I go 2s. 2s holds up how many? 2. Comes next, 2p. 2p can hold up how many? Well, it can hold up 6 electrons, right? But how many more do I need to get to the total of carbon? I only need 2 more, right? So 1s2, 2s2, 2p2. That's the electron configuration for carbon. Again, if you add up your superscripts, the 2 plus 2 plus 2, that adds up to the total number of electrons, which in this case is 6. When you say this, you say 1s2, 2s2, 2p2. You don't say 1s squared or 2s squared. It's not squared, it is 2. Okay, let's do zinc. Zinc is 30 electrons. Oh my goodness, let's start. 1s is the lowest sublevel. How many can it take? 2. Next is the 2s. How many can it take? 2. We're up to 4. Next, 2p. How many can it take? 6. So we've done 10 electrons so far. 20 more to go. What comes next? 3s. How many can it hold? 2. What comes next? 3p. How many can it hold? 6. How many electrons have we drawn? Add them up. That's 18. Okay, next is 4s. How many can it hold? 2. We're up to 20. What comes next? 3d. How many can it hold? 10. And we need all 10. Add all those superscripts together, you're going to get 30 electrons. Rubidium is next. Let's check how many electrons rubidium has. Rubidium is right here. Looks like 37 electrons. 37 electrons. So if you're doing a bunch of these, you can cheat a little bit, right? Because if we just did 30 electrons, that means we need to write the same exact thing with 7 extra. right? Because if we're doing 37 electrons. So I'm going to rewrite this. I'm going to copy it down. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Now, is that 3d filled? Yes, it is. If it was not filled, I keep adding to it until it fills, right? But it already is filled. The maximum it can hold is 10. We already have all 10. So far we've done 30 electrons. We need 7 more. So what comes after the 3d10? Well, then 4p comes next. And how many can 4p hold? 6. We need all 6. What comes next? 5s. How many can it hold? It can hold up to 2. But how many do we need? Just 1. You add them all up, you get 37 electrons. Last one's magnesium. Magnesium has 12 electrons. So we go 1s2, 2s2, 2p6. How many have we drawn? 10. 2 more. 3s2. And that is total of 12. 1s2, 2s2, 2p6, 3s2. All right, last thing we need to talk about is valence electrons. Valence electrons are electrons that are in the highest energy level. Electrons in the highest energy level. Remember, energy level N. So why are valence electrons important? Well, the valence electrons are the ones that are lost or gained or shared in order for a chemical reaction to occur. So they are extra important in chemistry. Now, if you remember, we can look at the periodic table and come up with how many valence electrons there are. Well, the reason we can look at the periodic table and figure it out is because of those electron configurations. So let's look at each of the ones that we did so far and try to tell how many valence electrons there are. Let's start with the oxygen here. So we say, what is the highest energy level? Remember, the energy levels are the numbers that we see here. So highest energy level looks like it's 2, the second energy level, right? So all these electrons would be valence electrons because they're both in the second energy level. How many total are there? Well, there are 6 valence electrons here. 2 in the 2s and 4 in the 2p. Okay, let's look at nickel. What's the highest energy level that you see? Again, remember the energy levels are the numbers that are down here. So highest energy level, highest number, that's 4, right? We have 1s, 2s, 3s, and 4s. So 4 is the highest energy level. It looks like we have 2 valence electrons. So my valence electrons actually come from these Offbot diagrams or electron configurations. We just use the periodic table as a shortcut. Okay, lithium. What's the highest energy level in lithium? Well, it would be the second energy level. And how many electrons are there? Just 1. So 1 valence electron. Carbon. How many valence electrons does it have? Well, what's the highest energy level? Highest energy level is the second energy level. These are all in the second energy level. So how many total? 4. These 2 and these 2. Zinc. What's the highest energy level, occupied energy level, I should say, in zinc? That is the 4th energy level, not the 3D, right? Even though it comes after, it's just higher in energy, but the highest energy level is the 4th energy level, not the sub-level, right? Energy level. And so there are 2 electrons in the highest energy level. Rubidium. What is the highest energy level that we see here? What's the highest number there? That's the 5th energy level, and it looks like we have 1 valence electron. Okay, magnesium, what's the highest energy level? The 3rd energy level here. Looks like we have 2 electrons in that highest energy level. Next lesson, we are going to be able to tell the electron configurations just by looking at a periodic table. It's pretty cool.